Alright, next video, we're going to do an application of the vector cross product here, and we're going to do it to find the volume of this strangely named shape, which is parallelepiped. So let me draw what this shape looks like. Okay, it's going to be a 3D shape. What I'm going to do here is draw a sheet of paper, and I'm going to put two vectors flat on the sheet of paper. Okay, so here's one vector, and here is another vector. Let me call these B and C. Okay, so these are flat on the sheet of paper. We have a third vector that is coming out of the sheet of paper. Okay, let's call that vector A. Now, if we take our first two vectors on the sheet of paper, B and C, and we make a parallelogram from those, so I'll copy this vector C over to the end of vector B. Let me see how that goes. Alright, it's vector C, I'll copy vector B over here. Alright, so I have a parallelogram, which is the base. And now I'm going to copy that parallelogram up to the top. This is going to be kind of a prism here. So here's vector B copied from the head of A. And let me just draw in vector A now. So this is the front side. Vector A should be parallel, not too bad. Okay, vector C over here. You can see it's kind of becoming a sort of cube-like shape. All of these sides should be parallel. This is vector B, and then in the back I've got another vector A. Okay, so I hope that is clear. It's sort of cube-like, although it's the angles are not necessarily 90 degrees. I mean, they could be 90. In this case, I'm drawing it so that they shouldn't be 90. So it's like a square, a cube that's been pushed over in two directions, so none of the angles are square. So we want to find the area of this. Okay, now this is basically a prism. This is an oblique prism. An oblique prism is one in which the base, so in this case, my base would be this bottom parallelogram. Let me point out. Okay, so this is my base, is the parallelogram on the bottom. So a normal prism, you have your base, and then directly above that is your the other face, the copy of the base. Or in this case, it's shifted over. Okay, normally, because normally the sides are 90 degrees, but an oblique prism, it's shifted over, but it still works the same. It's just you have to use the perpendicular height rather than the length of vector A. So let me say, okay, this vector here, let's say this is perpendicular to my sheet. So I have an angle here, theta. Okay, so this is, and if I make a little triangle here with my vector A, okay, this side here is my vertical height of my parallelepiped. Okay, so my volume is the area of the base. So volume per prism, area of base times the perpendicular height or vertical height. Okay, now this vertical height h that I have, my height, if I look at that triangle and I use my trig rules, it's going to be the magnitude of vector A times the cos of that angle. That'll give us the perpendicular height. Okay, now if I times both sides of this equation here times both sides by b the vector cross product of B and C. Okay, the magnitude of that cross product. Now remember that cross product, this is the area of the base. Alright, and this is also, this also refers to this vector here, because that perpendicular, it refers to the length of that vector. That is my cross product. My cross product has that. The magnitude is the area of the parallelogram, and the direction is perpendicular to the page. So that's the length of that side. Alright, so if I multiply both sides of this equation by the length of that side, the B dot C, and over here I'll put it like this. Okay, so this, on the left side, now I've got the height times the base. This is base times height. So this is the volume of my parallelepiped. On the right, if you look here, this is the dot product formula. And it's the dot product of A with the vector B times C. Okay, so the volume of this parallelepiped has this very nice formula, and that is it. And although actually we don't even need to have these brackets here, so if you think about it, just rewrite that, and you can pause for a minute and think about this if you like. Order of operations, will I do this first, the dot product first and then the cross product, or will I do the cross product first? And is it possible to do to take a pick? So you could, what you do is pause a minute, think about that, and okay, you paused, got back. Okay, the thing is, if you were to do the dot product first, this will give you a scalar, just a number, which you cannot do the cross product of that with C, okay, with another vector. So that means that you have to do, must do first. So we don't need to specify brackets, because there's only one way you can actually do it. Okay, so now, so our volume is this, but what is now a nice way to do this? There's a nice easy way to do this, and that is remembering the fact that B cross product with C equals I, J, K, and let's just say B1, B2, B3. This is assuming that we've got our I values, B1, our J values, B2, and we've got our K value, B3, and so on. And C1, C2, C3, same thing. C2J plus C3K. Alright, so now we have to do the dot product of A with this. Okay, and then if you remember, if I'm doing dot product, for example, if A is, let's just stick to these general things at the moment. And if I wanted to say do the dot product of A, of this A here with B, dot product B, I just times the number in front of the i's together. Okay, so that would be A1, B1. Okay, so just look at the I here and the I here, and I times those numbers together, and same with the J's. Okay, A2, B2. Okay, so what it boils down to, and it would be good to think about this, is that I can actually just replace the I, J, and K up here with my A1, A2, A3. Keep everything else the same. Alright, so this is actually a very nice, simple formula. If you think about, have a think about why I'm able to replace that top row like that. You can ask me in class. So for example, if I had, let's just make up a couple of vectors. 2i minus j plus 3k. B equals 3i plus 2j minus k. C equals negative I plus 4j plus 2k. So if I want to find the volume of the parallelepiped with these, formed by these vectors, so volume equals A dot B times C, which is just going to equal, I can just put these numbers in, 2 minus 1, 3, 3, 2, minus 1, minus 1, 4, 2, and just find this determinant. It's just a simple determinant, which, let me just do it, if you remember the way I showed you last year. My little trick that I like to do is just add on the first 2 rows and do this. Times these and times these, and so purple and the green, so the purple ones I times together and I times together, these ones then are plus and these ones are minus. So 2 times 2 times 2, I've got 8 plus the next purple, negative 1 times negative 1 times negative 1, so that is minus 1. Then 3 times, can you read that number? 3 times 4, that's 36. And then the other ones are minus them. So I'll just put it in brackets, I'll minus this whole thing. Minus 1 times 2 times 3 is minus 6. 4 times 2 times negative 1, minus 8. 2 times 3 times minus 1 is minus 6. So I've got 8 minus 1, 7. I've got 43 minus a negative 20 plus 20. So I believe I get 63. And we don't have any units, so we can just call this, not square units, cubic units. And oh, this is kind of interesting. This method that I found when I was at university, I came up with this. I just thought it was a little bit simpler. I mean, it's not very difficult to figure out, but I just came across on the internet. It's actually got a name. Somebody else had come up with this in like 1860 something, and it even has a name. I don't know if they had a time machine and copied me or what. Anyway, video finished. See you Monday.